Kia ora. I'm Gabriel, and today I'll be presenting our project, which is the building and testing a motor power analyzer. This project took place in Toyohama Institute of Technology in the May campus, and this project has been done together with my group mates, George and Sushant. I also want to thank Sir Priyank and Sir Shane for their help throughout this project. So, yeah, let's get into it. So, um, electric motors are major energy consumers in industrial systems. So we all know that electric motors has been widely used worldwide, but what we don't know is that how electric motors are going during their operation, and how can we prevent failures and monitor the motor during operation. So yeah, in this presentation, I will talk about and give a bit of learning about the power analyzers. So yeah, let's get into our motivation to create a practical learning platform that demonstrates real-world motor monitoring, protection, and power quality analysis using industry standard hardware. Let's go to the problem statement. Integrating the power analyzer, the relay, and the contactor. Fully functioning system required precise wiring, testing, and data acquisition. Communication issues with the relay and limited lab time added changes challenges. Our objectives is design system schematics and project schedule through the Gantt chart, wire and assemble all components safely and correctly, which includes all the wiring of the power analyzers, current transformers, relay, and the contacts, and test the control circuit between the relay and the contactor, and acquire electrical data using the power analyzer, which displays all the acquired values, including voltage, current, power factor, THD, total harmonic distortions, and the apparent power, active power, and reactive power. So, and produce full documentation of the project. Yep. So, about the literature review, I've searched, I did my research, and I've found about this device, the Fluke Power Analyzer. It really did. It really does the exact thing that the ION 8600 of Skydner Electric. It reads the voltage, current, power factor, harmonics, and transients to assess motor performance and efficiency. So the modern digital power meters and power quality analyzers, for example, the ION 8600, use high resolution ADCs, DSP, and high speed sampling for accurate real time monitoring. According to Fluke, motor power analysis focus on measuring voltage, current, power factor, harmonics, and many more. NILM traditional analog meters are available but lack precision and advanced diagnostic um, capabilities. Let's jump right in the gaps and limitations. This is quite a lot of limitations in the current systems. This includes the traditional meters cannot measure harmonics, transients, or provide detailed motor diagnostics. Unlike those modern power analyzers like the Fluke, the ION 8600, or Skydner Electric, like they display the voltage, current, and power factors, THDs, and many more. And NILM techniques cannot deliver phase accurate or motor specific insights, communication failures, noise, interference, and calibration drift affect measurement and accuracy. Dynamic and harmonic rich environments, for example, motors with drives. require devices capable of handling fluctuating loads and power electronic distortions. Yep, so how this project addresses these gaps? Integrates a high accuracy industrial power quality analyzer or the ION 8600, the motor protection relay, and to create a complete real world monitoring system. Provides precise measurement of the voltage, current, harmonics, power factor, and energy use features missing in basic meter and NILM. Establishes a practical, testable educational setup for understanding modern motor analysis tools. Demonstrates hands-on wiring configuration and data acquisition using industry standard hardware, bridging the gap between theory and operational practice. And system design and methodology. So, the black diagram of the system. The system consists of three main components, which is the power analyzer, which is the ION 8600, the LTM R08 EFM, which is the relay, and the LD, oh, sorry, and the LC1 D09, which is the contactor. This this also supported by three CDs, one voltage transformer, which supplies a 230 volts, and then stepping it down to 110 volts, and that feeds the um, power analyzer. CD feed current signals into IO and 600 voltage input supply by phase to neutral. LTMR output controls RSC1 D09 for motor switching. So this relay and um, contacts contactors setting is for the safety of the power analyzer and the motor. Let's jump right in. The Yep, so let's jump right into the tools and components used, which I've already mentioned before. The ION 8600, which is the most important component in this project. It measures harmonics, THD, power, kilowatt hours, events, and even those faults that can be detected through the motor protection relay, the relay which acts like the brain of the system and decides which faults to trip. And once a fault occurs, the LG1D09 contactor will open the circuit, which turning off the motor. So the current transformers, the three current transformers, which has a 305 current ratio, and enclosure, the test point, which is the one we use to test the connection between the relay and the contactor, and 110 volts control power supply derived by the 230 volts power supply. So project management tools like Gantt charts and then reference materials that we use into the literature reviews and some photos from the internet. Yep. So let's jump into the system methodology, the design approach, hardware and software. So hardware approach, which is the step-by-step engineering workflow. First is um, we the knowledge acquisition, which where we completed all the information we need before starting the project and collecting what we need for that specific day whenever we're doing a activity every week. So after the um, knowledge collecting, we're up on the planning, which is the Gantt chart, which is the step by step process until we finish the project, and then down to the documenting the original setup, which where we started to took the original setup out the original. place. So wiring the new system, which we started wiring the current, no, the relay and the contactors, and the stage testing, which is the last testing. So constructed using SCADA electric components to meet industrial wiring standards. So for the software approach is the SoMove software, which we use for the programming. Let's jump into the control circuit flow. So the 230 volt supply down to 110 volts by the voltage transformer down to which feeds the relay, and the relay feeds the contactor during normal condition, and then it goes right up into the motor. While during the fault condition, the relay will decide to trip the circuit and then um, sends the signal to the contactor, which opens the circuit and turn off the motor. So let's jump into the measurement flow. So as we can see in the picture, there is a red, white, blue wire on the on the right hand side of the um, power analyzer. So the ones underneath is for the current transformers, which will go into the secondary winding of the current transformers. The ones above is for the voltage transformers. And the ones on the left hand side if, is the neutral and ground. The green is for the neutral and the black is for ground. And the blue, white, red will go on the current transformers primary winding. So yep, let's go to the implementation overview. The practical integration of the power analyzer with the relay motor management system included removal of the old analyzer enclosure, preparation, wiring, and testing. So a step-by-step development process conducted initial documentation and safe removal of the existing system, which we filmed the removal of the existing system and took documentation and listing all the values that we need, taking a photos on the original wiring so we can compare it into our results and follow Gantt chart milestones with flexible time management. Yep, so initial system documentation and removal. Inspected and photographed the existing power analyzer as I've mentioned before, and logged baseline readings and configuration settings, applied full safety procedures like we turned off the whole system before we taking the power analyzer out of its original place. So enclosure preparation and component mounting. So this just talk about the size of the enclosure, which has a 33 cm long, 25 centimeter wide, and 25 centimeter tall. And there is this DIN rail which holds both the relay and the contactor together to avoid the parts moving inside the enclosure. So it has 30 cm long as well. Yep. So control circuit wiring. The control circuit refers to the relay and the contacts. So this prevents any faults into the motor and power analyzer. Current transformer CD integration, which steps down the current that feeds the that being fed into the power analyzer. Programming challenges and resolution. So we did have this one um, problem, which is this software. We didn't manage to program because there's a problem in the CD itself or the relay itself, the LTM R08 EFM. So, and at the beginning, the SOMove don't have the option to program the relay. So the ID guys fixed this immediately, but um, after this got fixed, we came into Toy Homai to start the program, but another problem came in, which is the software don't recognize the relay device. And then I've tried to buy another cable, but it still don't recognize the software of the device, which is the relay. Yep. So the time management as well, which is the is scheduling the Gantt chart. We haven't followed it because we have our own commitments, which avoids us to go to the development of the project. And then, sorry, and then we have managed this because we have managed this time management problem because during semester break we are going to Homai to just um, do a little bit of progress in the project, and during weekends, integration of hardware and software. Hardware successful integrated the relay and the contact CDs and the power analyzers. Results and testing overview. One, ION 8600 used to measure motor electrical parameters under load. So we have connected the power analyzer into the load just to see how it behaves during operation. And yep, we've got our expected values except the THD. Result and testing. So this is what we've got on the demand metrics. So kilowatt hours, which is the active power. This is what we got. The 2000 for the this is the active power, the 2014 kilowatt hours, and the 4494 kilo kilowatt hours, which is the reactive energy. The peak demand is low. Oh, the the active power and the reactive power is high because the peak demand is just 0.06 kilowatts, which is normal if the peak demand is low. The reactive power and active power will be high. So this is the electrical parameters. The voltage phase A, B, and C, which is roughly around the 230 volts, which meets our expected values, and then the current as well, and the frequency, which is 49.9 hertz and not too far from 50 hertz. Challenge phase, this is the technical issues for the LTMR, which we could not connect into the software, and the IT problem, which the software don't have the um, choice choice for us to be able to program the relay. So we've overcome this by by interpreting THD as a load related effect or not a measurement error, emphasizing proper power quality assessment. Logical time management issues, which I have been talked about earlier. So there's limited access to H10 lab and personal schedule conflicts restricted project progress, and extended work sessions into semester breaks and weekends. So every semester break and weekends, we always go to Toy Homai just to do a little bit of progress in the project. Conclusions summary: successfully designed, constructed, and wired the power analyzer systems and the relay and the contacts in a secure enclosure. Yep. So every components we've got has a enclosure which makes them safe from any dust or weather differences. And then analyzer provided stable and accurate readings of voltage, current, frequency, and power quality. So by getting this accurate readings, um, the same readings from our expectations, the voltage, current, frequency, and power quality match our expected values, except the THD width is a little bit too high. And overcame time management challenges by dedicating extra hours completing project milestones on schedule. So, key takeaways: gain hands on experience troubleshooting LTMRO8 EFM communication failure likely due to hardware fault. So this project is a really big help for us students because we've gained a hands-on troubleshooting and wiring of the physical components and electrical field. So this is going to be a big help for us. So the high stage, the 24% under load highlighted the real impact of harmonics and motor operation, reinforced the importance of considering load-related harmonics in power quality assessment. The future scope improvements, fault isolation, and LTMRO8 EFM replacement. So I think by replacing the relay, it will allow you guys to, for the next students to able to be able to program the new relay and complete the project and try the full load testing and THD verification. So by replacing this relay, you can also verify the THD, which we got 24%, which should be below 5 or 10 or 15%. So HMI's card integration use the Power Analyzer Modbus or Ethernet to enable remote monitoring and logging, which can be done as well in HMI. And power factor correction study use reactive energy data to implement a small capacitor bank and improve system efficiency. So yep, that's all my reference. That's for the equipment and literature reviews and the others like photos that we got from internet. Thank you. And if you got any questions, please feel free to ask. Thank you.